All right, everybody, welcome to the video here for lesson number 6 on probability rules. We're actually going to spend 2 lessons developing some ideas about probability rules. In today's lesson, we're going to kind of review a couple things that we've already learned about probability. We're going to introduce you to the first of a few probability rules in this lesson. So first, the opening exercise. So it tells us that we have a randomly chosen adult from the United States. It says to define event A as the person is male and event B that the person is pregnant. Are the events A and B mutually exclusive? Are they independent? Explain your reasoning. So in this particular case, event A being male and event B being pregnant cannot happen simultaneously. So these events are what are known as mutually exclusive. Because a male cannot be pregnant. There's your answer. And there's another way of showing mutually exclusive. Now, if two events are mutually exclusive, does that mean whether or not they are independent? That's a question more for AP stats. So we're not going to develop that idea here today. Just understanding that we're talking about mutually exclusive events here is important. So in the previous lesson, we learned that there's a complement of every event, meaning it's the not event happening. So the probability of it raining and the probability of it not raining, they always add up to 1. So one of the things that we have to understand about a complement is the probability of an event happening plus the probability of that event's complement, or it not happening, is always equal to 1. There's a 60% chance of rain, that means there's a 40% chance of not rain. So in this particular example, it talks about a flight being on time. The probability of that is 0.78, or 78% chance of being on time, and it wants us to find the complement. So the complement of this flight being on time is going to be 1 minus 0.78. So the probability of the complement happening is going to be 0.22. And what that means in the context of this problem is there's a 22% chance the flight is not on time. Explain why event A and event A complement are mutually exclusive. So these two events is another example of two events that are mutually exclusive, because a flight can't both be on time and be late at the same time. So you can say a flight cannot be on time and not on time simultaneously. So what we're developing here is the idea that an event and its complement are always going to be mutually exclusive. This is an important concept in Algebra 2. Understanding that means you understand what mutually exclusive means for this course. Moving right along. So here we're going to kind of just review a couple things. So here's a probability question. It says, when a room is randomly selected at a downtown hotel, the probability that the room is a king-size bed is 0.62. We're going to call that K for king size. And the probability the room has a view of town square is 0.43. We're going to call that probability V. So right now we know the probability of being a king-size bed is 0.62, and the probability of that room having a view of the square is 0.43. Those are the two probabilities we currently know right now. It says the probability of both having a king-size bed and a view of town square is 0.38. So the probability of a king bed and having a view is 0.38. So it tells us to let A be a king-size bed, so all these K's will change to A's. And having a view be event B, so we'll change all these V's to B's, because they tell us what variables to use, so we want to use those. It says create a Venn diagram for this model. So if we're creating a Venn diagram, we start with our square to represent all the different probabilities that can occur. I have one circle for event A. I know these circles are going to intersect because there is a chance of them happening together, meaning these are not mutually exclusive. And the first probability we want to put into my Venn diagram is the probability of A and B happening. So I'm going to put 0.38 right in there. Then if we do some quick calculating, so if I do 0.62 minus 0.38, we'll figure out the probability of just having a king-size bed without that wonderful view. If we take 0.43 and subtract 0.38, I get 0.05, so that would be the probability of having that gorgeous view but not having a king-size bed. Then if I take 1 and subtract the 3 probabilities I now know, we can figure out what's the probability of having neither of these, which would be 0.33. Now, if you don't like Venn diagrams and you'd rather be a hypothetical two-way table person, you can do that too. So we can create a hypothetical two-way table here. So I'm going to make my rows A and not A. Whoops. So king size bed or not a king size bed. I'm going to make my columns B and not B. And we want to make total, so I need a little bit more space here. Since it's a hypothetical 1,000 table, the ending number is 1,000. Probability I want to start with is A and B, so this first cell or this first box. 38% of 1,000 is 380. It tells us the amount of king beds that there are is 0.62, so there's 620 king beds in this hypothetical 1,000 situation. So if I do some quick subtraction, 620 minus 380 is going to be 240, so we now know that there are 240 that go in that box. That's this percentage here in your Venn diagram. I know for the rooms with a view, there is 430. So the B column should be 430. If I subtract these two numbers, I get 50, which would be this percentage here. And to have neither of those two things, right, we would do some subtraction. We could figure out that this is 480, do some more subtraction, not 480, 380. That was bad math. So we can figure out that this box is 330. Notice that percentage matches this percentage. And then if we add our columns here, we have 570. Now, there are pros and cons to both. The Venn diagram is a quick visual, and you can see kind of where all your percentages are. But if you notice, the hypothetical 1,000 table does give us a little bit more info. Like, I know how many total rooms do not have the view. I know how many total rooms do not have the king-size bed without having to do a bunch of different addition and subtraction here with our percentages. So, it says, find the probability of A given B to the nearest 1/10 of a percent, and what's the meaning of this probability? So the probability of A given B is equal to the probability of A and B divided by the probability of B. This is a rule that we went over 2 lessons ago. So we know the probability of A and B happening, that was 0.38. The probability of just B happening, that was 0.43. So if I do 0.38 divided by 0.43, I wind up getting a 0.8837 number. Now it says percent, so I want to convert this. So there's an 88.4% chance. Now, to interpret that in the context of this problem, what this is saying is the probability of having a king-size bed, given the fact that you already have a view, is 88.4%. Meaning, there's an 88.4% chance if you're sitting in a room with a view, you have a king-size bed. Okay? So we can see that that percentage is pretty high, meaning this hotel probably gives a lot of the king-size beds to the rooms with a view, which kind of makes sense. Are the events A and B independent of each other? Well, to prove independence, we already know one way of proving independence. Independent events, the probability of an event given the other event is the same as the probability of the event just happening. Meaning, by introducing the other factor, in this case, having a view, the probability of having that king-size bed remained unchanged. Meaning that there was no correlation between having a king-size bed and having a view. So we know the probability of having a king-size bed given a view, we just found that, was a 0.884%, 88.4%. The probability of just having a king-size bed, nothing else, was, if I'm remembering correctly, yes, 0.62. These are not the same, therefore these are not independent events. Now again, it says justify your answer. What does this mean? So this means that the idea of having a king-size bed is not affected, or I'm sorry, is affected by whether or not you have a view, right? I'll say that again because I stumbled on my words there. So the probability of having a king-size bed is dependent upon whether or not you have a view, right? So the view and the king-size bed have some type of correlation. There's no independence there. All right, let's try another one. So here we have this credit card company. It tells us that there's a 42% chance that they have a long-term card holder, a 35% chance that they pay their bills in full, and a 23% chance that they have a long-term card holder who also pays their bills in full each month. It tells us to make L the variable for long-term card holders and F for paid in full. And it wants us to make a Venn diagram for this. Chances are, if I give you a question, I'm not going to have you do one or the other. It's going to be your choice. Like, how are you going to do this if you were to do this on your own, right? Are you going to be a Venn diagram person, or would you rather make a two-way table, right? So it says 23% are card holders who also pay their bills in full. That's end, so that's going to be where these two things overlap. So that's going to be 0.23. Notice I'm not using percents here. I'm changing them to decimals. We like that better in our Venn diagrams. So for the long-term card holders, if I subtract 42 and 23, I wind up getting 19%, so I'll put 19% in here, knowing that that whole circle still adds up to 42%. And if I do 35 minus 23, I wind up getting 12% for the people that pay in full that are not long-term card holders. And if I do 1 minus those 3 percentages that I now know, we can figure out how many are neither of these two people, right? How many people are not long-term card holders and also do not pay their bills on time. It then says compute the following probabilities. Probability of L given F. So the probability of L given F is the probability of L and F divided by just the probability of F. So the probability of end is 0.23. The probability of just being F was 0.35. Divide those two decimals because we know the rule. So all we're doing here is calculating. And it says to compute the probability to nearest thousandth. Notice this one does not say percentages. So we'll say that this probability is 0.657. Then it says, compute the probability of F given L. So to find the probability of F given L, we would say the probability of F and L divided by the probability of L. These are different. Because these are different, they should come out to be a different number, right? We're dividing out a different probability in the denominator because of what was given or what was known in the problem. So the numerator is going to stay the same. It's still going to be 0.23. That's not going to change. But the denominator is going to be the probability of being a long-term card holder. So that was 42% chance of happening. So if I do 0.23 divided by 0.42, I wind up getting a decimal here of 0.548. I like to put the zeros in front. It makes it look neater. So we have this decimal and this decimal, two different probabilities using the same two variables. It just depends on what is given here. Now, there's a lot of things that you can now do with this knowledge that you've just created. For this class, the only thing we need to do is be able to figure out these two numbers. But in AP Stats, you'll go a little bit deeper, and you'll be able to determine that there's a higher percent chance of L given F, and what does that actually mean in the problem, right? So for right now, finding these probabilities is good enough. Are the events independent of each other? So we've already found two different given probabilities, so let's just pick one to use. So say, is the probability of L given F the same as the probability of just L happening? meaning by introducing the outside factor of f being a full-time pair, right, we don't have a change in probability. So we already know this probability is 0.657. The probability of being a long-term cardholder was 0.42. Those are definitely not the same. Therefore, these are not independent. Because these are not independent, what we can do here is we can talk about how these are dependent upon each other. So it says to use two different methods to justify your answer. So what you could say here is this, or you can say, what is the probability of f given L, and is that the same as the probability of f? Well, we figured out this probability was 0.548. The probability of f was 0.35. So again, not the same. So depending on which one you choose, you're going to get to the same result, which is that they are not independent, or that they're dependent upon each other. So there's some type of a link between whether or not you're a long-term card holder and whether or not you pay your bills in full, according to this credit card company. All right. So now we have to talk about a rule. So our new probability rule that we're learning today is how we can quickly compute the probability of A and B if and only if the events are independent of each other. This must be true. To use this example. So how can we quickly compute these probabilities? Now, this is something that you actually did way back when you first learned probability in like 7th grade. When your teacher said, I'm flipping a die and I have a chance of landing on heads is 1/2, and I'm rolling a die and there's a chance of landing on the number 2 is 1/6. What's the probability of both happening? You multiplied those two numbers together. We even did that earlier in this chapter. Well, it's the same exact thing that we're doing here. So the probability of the event A and the event B happening is the same as the probability of the event A times the probability of event B. Again, this only works for independent. So either they have to tell you that the events are independent, or they have to give you context that helps you prove or show that the events are independent of each other. So when you're reading through a problem, if you feel like the two events that they're describing are independent of each other, then you can definitely use this rule. If you don't know that, you have to make a two-way table. You have to go through the whole process to figure out the probability of A and B happening. Okay? So let's take a look at one that is an obvious set of independent events. It says a number cube has faces ordered 1 through 6, and a coin has two sides labeled heads and tails. The number on a cube will be rolled and a coin will be flipped. So think about this. If you have a die in your hand and you have a quarter in your hand, if I flip the quarter and it lands on heads, is that going to affect the number that I roll on my die? The answer is absolutely not. It can't. Whatever that coin lands on is not going to change the chance that I roll a 6 on the die. So these events are independent just by the context of the problem. I don't have to do any math. I don't have to do any proving. I'm saying that these are independent events because the probability of the coin will not affect the probability of the cube or the die, or vice versa. So what is the probability of rolling a 4 and flipping heads? So the probability of rolling a 4 and landing on heads is the same as the probability of rolling a 4 times the probability of landing on heads. The probability of rolling a 4 is 1/6. The probability of landing on heads is 1/2. Multiply those out, I get 1/12. If I like that better, if I like decimals better, I could say 1 divided by 12. I should know that, but it's late. So we'll say that this is 0.083. So there's about an 8% chance of both of these things happening at the same time. It then says you toss a coin 5 times. What is the probability? That should say you will see a head on all 5 tosses. So that is the probability of heads and heads and heads and heads and heads. Whew. So if I do the probability of heads times the probability of heads times the probability of heads, 5 times, this will be the probability of rolling heads 5 times in a row. Notice this is not saying that you have a coin and we want to flip it 5 times. What's the probability of landing on heads just that 6th time or that 5th time? This is saying I want to know the probability of landing on heads all 5 flips. So the chance of that is probably pretty small. You can do it by multiplying, or if you're really smart, you can say it's really just 1/2 to the 5th power. Makes it a little bit easier to type into your calculator. And we get a 0.03125 chance of happening. So there's about a 3% chance of happening. Okay? So then it says, if you toss a coin 5 times and you got 5 heads, would you think that this coin is fair? I would say probably not. Because there is only a 3% chance of this happening. And we'll see actually in the next chapter, when we dive a little bit deeper into statistics and probability, that we can actually prove whether or not that this coin is fair or not, or at least get a pretty good idea of whether or not it's fair or not. For right now, I'm just asking you to think. If I said that there's a 3% chance of happening, would you think that that's likely or not likely to happen? I would say it's probably not likely to happen. Could it happen? Sure. Chances are it probably won't, though. Number 5 says a particular spinner, the probability of red is 0.25. If you spin the spinner 5 times, what is the probability that it never is on red? That should say red, not read. So the probability of landing on red is 0.25. So the probability of not red is 0.75. So the probability of not red 5 times is 0.75 times itself 5 times, or to the 5th power. So if I do 0.75 to the 5th power, I have a pretty good chance of this happening. So there's a 0.237, or about a 23.7% chance of happening. Seems somewhat likely, right? If I said there's a 23% chance of something happening, that's a lot more likely than 3%, right? Again, don't get caught up in what's likely and what's not likely. That's for another lesson. For right now, I'm just happy if you're able to find these probabilities and you're able to see that this new rule allows us to multiply independent probabilities. Now, the one thing that I did not talk about with this last question is whether or not the probability of landing on red or not landing on red are independent of each other, and they are. Think about it. If you have a spinner and you have green, yellow, and red, if you spin it, the probability of landing on red is going to be independent of the probability of not landing on red, because you can't possibly do both of those in one spin. Okay, so probability of red and not red cannot happen here. So these are two events that are definitely going to be independent of each other. So now that we know the rule, we should be able to move forward to our homework. So here's a good chance for you to pause the video, take a couple minutes, try the homework questions, and then come back and see how you do. All right, number 1 says, of the bulbs that are available at the store, 42% are fluorescent, 23% are long life, and 12% are both fluorescent and long life. So I'm going to use this as F. They don't tell me what variables to use, and I'll do this as L. So again, here is an example where I'm not telling you what to do. If you made a two-way table, awesome for you. If you made a Venn diagram, awesome for you. It all depends on what is best fit for you, right? I tend to like two-way tables a little bit better, only because they give me a lot more info, but whatever you did is probably fine, okay? So let's make a quick two-way table here. So we have the probability of being fluorescent or not fluorescent, the probability of being long life or not long life. I put those in the wrong spot. Long life, not long life. I don't need this last row. Well, that's not working for me. Let's see. Let's make this a little bit better. Here we go. Okay. Good. So I'm going to make a hypothetical 1,000 table here. I don't know how many bulbs are here, so I'm just going to guess it's 1,000. 42% of them are fluorescent, so that would be 420, which would leave 580 to be not fluorescent. 23% are long life. That's 230 bulbs that are long life, making 770 not long life. It also says that 12% are both. So that would be 120 bulbs that are both. I could do some quick math here, do some subtraction to get 300 here, to get 470 here, and to get 110 here. So now I know everything about this table. It then says a light bulb will be selected at random, and it says rounding your answers to the nearest probability for a nearest thousandth for your probability. So the bulb selected is not fluorescent. We know that there are 580 out of 1,000, so the probability of not fluorescent is going to be 580 out of 1,000 for my table, so that's going to be 0.580. Probability of the light bulb is fluorescent given that it is long life, so the probability of fluorescent given long life, so that would be the probability of fluorescent and long life divided by the probability of just being long life. So the probability of end, we knew the probability of end, they told us it was 12%, so 0.12. We knew the probability of long life, we don't even need a table for this, was 23%, so that's 0.23. If we wanted to use a table for it, we could. So we have 0.12 divided by 0.23, and we get 0.522. There we go. Then, are the events fluorescent and long life independent of each other? Well, since we've already found the probability of F given L, let's see if the probability of F given L is the same as the probability of F. Meaning by introducing L, the probability changed or didn't change. So since I already know the probability of F given L, 0.522, and we know the probability of just being F was 0.42, we can see that there is definitely some dependence here. So these are not independent, meaning the long life bulbs affect the chance of the bulb being fluorescent. So the chances here are changed. This has been changed. Okay. Number 2, Josie will soon be taking exams in both math and Spanish. She estimates that the probability she passes the math exam is 0.9, and the probability she passes the Spanish exam is 0.8. She is also willing to assume that the results of the two exams are independent of each other. So that part there where it says that these two exams are independent of each other, that means that there's no effect on whether or not she passes math and whether or not she passes Spanish. Right, so there's no effect there. So because these two exams are independent, the probability of A and B can be calculated by multiplying the probability of A times the probability of B. We're using that new rule that we learned in lesson 6 here. So it says, using Josie's assumption of independence, calculate the probability that she passes both math and Spanish. So the probability of passing math and Spanish is equal to the probability of passing math times the probability of passing Spanish. Well, the probability of passing math was 0.9. Probability of passing Spanish was 0.8. So we wind up getting 0.72. So there's a 72% chance that she passes both tests. It then says, create a Venn diagram using M for passing math and S for passing Spanish. So if we make our Venn diagram here, math, Spanish. We already know what number goes in the middle. We found end is 0.72. Now the probability of passing math was 0.9. So this whole circle has to represent 90%, right? So 90% chance. So if I subtract 90% and 72%, that's left over of 18%. This whole circle has to be passing Spanish. Well, passing Spanish was 80%. Well, since 72 is already being used, this is going to be 8%. And if I do some quick calculating, so if I do 1 minus 0.18 minus 0.72 minus 0.08, we wind up getting a 0.02% chance, so a 2% chance that she passes neither and fails both of them. Good for Josie. So, are the events M and S mutually exclusive? The answer here is no, because these events can both happen at the same, I'm having trouble spelling tonight, same time. A Venn diagram that would be mutually exclusive would look like this. They would have no overlap. So for this last question, again, not really on the level that we need to get to here, a little bit beyond. If you're a accelerated student, this would be a really good thing to Google, especially if you're taking AP Stats next year, or even if you're a Regents student and you're taking AP Stats next year. It's kind of easier to explain using some visualization. If we were in class, I'd be able to totally explain it to you. Kind of hard to do over the internet here. And since it's not a huge and important part of this course, I'm never going to ask you about it on a problem set or anything like that. We don't need to go ahead and do it. But if you are interested in it and this is something that's intriguing you, go ahead and Google it and you could totally find out if independent events can be mutually exclusive. The answer is kind of vague, which is why I'm not getting into it right now. So hopefully this video helped. Make sure that you are checking off that you turn this in on Google Classroom, and hope to see you soon.